Hello everyone, welcome to our Group 7's presentation. Today we are going to discuss about case study 2, discussing about adaptive classroom lighting system. I am Erika Unardi with my group mates Devina Khalista Hindarsono, Muhammad Tristan Aitayla, and Najma Zahira Chahyani. First and foremost, for the background of our case study is that lighting affects classroom visibility, comfort, and energy used, but conditions often change throughout the day. Rooms can become too dark during cloudy weather, while lights may stay on even when daylight is already sufficient. This case study proposes an adaptive system that adjusts roller blinds and lamp brightness to maintain comfortable lighting while improving energy efficiency. So for the components, we have an indoor brightness sensor, an outdoor light information or sensor, automatic roller blinds, and also lamps with adjustable brightness. So for the goal is to maintain optimal classroom brightness, reduce energy use by prioritizing daylight, and adapt automatically to changing lighting conditions. So this is the overall program that we have coded in Google Colab. So we based off everything from our study case 1, from the pseudocode and the flowchart. And the first in the code is a constant threshold number from our pseudocode. So we can see here we put a constant for our outside light when it's high, which is 800 lux, outside light when it's medium or comfortable, which is 400, inside light when it's dark, which is 300 lux, and inside comfort light for 500 lux. And then we store them into a data storage to save our results using history. And in the logs, this will be the list to hold each round's data. And then next we use function. We use function which is using def to decide the blind position. So in this function we also used if else, and then return. So it's also a function with conditions and a return function. And in here we determine the blind position based on the outdoor light. The next function is the function for deciding the lamp level from the indoor light, using if else, and return. And after that, we apply the lighting, we apply the blinds and the lamp level using another function, code, to return the final combination. After that, we ask the input from the user. So they can input data for 3 loops, because in real life, we need a monitoring system that will always monitor continuously for the ever-changing weather. But in our case, we use a loop 3 times, although in real life, it should be more than that. So we ask the user to enter their data for 3 loops, which is the input. And then we now use the looping code. So for the looping code, we use for. And this will continue for 3 times, where the user can input the outdoor light value and then enter the indoor light value. And then the function will run, and it will run the current blind, the current lamp, and then the action that needs to be taken. After that, we will create a simple row dictionary to save it into our history.
Hello, my name is Devina Khalista Hindarsono, and next I will explain the overall program. So the purpose of this project is to simulate how a classroom lighting system can automatically respond to changing environmental lighting conditions. The system uses outdoor and indoor light intensity data to determine the most appropriate blind position and lamp brightness level in order to maintain visual comfort inside the classroom while also improving energy efficiency. At the beginning of the program, we define several constant variables, namely out high, out med, in dark, and in comfort. These variables act as fixed lighting used for system decision making. The first one is out high, 800, means outdoor light above 800 lux is considered too bright. The second one, out med, 400, represents medium outdoor brightness. The third one, in dark, 300, means the classroom is considered dark below 300 lux. And the last one is in comfort, 500, represents uncomfortable indoor lighting conditions. These values are important because they become the environmental standards used throughout the entire adaptive lighting process. Next, the program creates a dictionary called history. Inside this dictionary, the program stores the first one is the classroom name, and the second one is a dynamic list called logs. The purpose of the logs list is to save all simulation results generated during the program execution, allowing the system to keep a record of every light conditions and adaptive response. The program is then divided into several functions to make the system more modular and organized. The first function is determine blind, kurung buka, kurung tutup. This function receives outdoor light intensity as input and uses conditional statements such as if, elif, and else to determine the appropriate blind position. The logic works as follows. The first one, if outdoor light is very high, the blinds are fully closed. If outdoor light is moderate, the blinds become half open. And if outdoor light is low, the blinds are fully open. The second function is determine lamp, buka kurung tutup kurung. This function analyzes indoor light intensity and determines the lamp brightness level. The first one is dark classrooms, activate high lamp brightness. The second one is moderately lit classrooms, activate medium brightness. And the last one is sufficiently bright classrooms, turns off the lamp. And the third function is apply light, buka kurung tutup kurung. This function combines the blind positions and lamp brightness into one readable output so the user can clearly understand the final lighting response generated by the system. After defining the functions, the main program begins by displaying the system title and target classroom location. The user is then asked to input outdoor and indoor light values. The program uses a for loop to repeat the simulation 3 times. This loops represents repeated environmental testing scenarios. During every iteration, the user inputs sliding data, the values are converted into integers using int buka kurung tutup kurung, the adaptive functions process the environmental conditions, and the final lighting response is displayed. The program then creates a dictionary called row. The dictionary stores the loop number, outdoor light intensity, indoor light intensity, blind position, and also lamp brightness level. The data is then appended into history logs, allowing system to dynamically accumulate all simulation records. Finally, another loop is used to display the final summary logs. This summary shows all environmental lighting conditions together with the adaptive response generated during each simulation loop. Through this process, users can evaluate how the system responds to different classroom lighting scenarios. So lastly, this project implements the first one is input and output programming, the second one is condition selection using if, elif, and also else, the third one is static and dynamic data storage, the fourth one is iteration using loops, and the last one is modular programming using functions. We don't use OOPEC. Also, this project demonstrates how Python programming can be applied to create a responsive environmental system capable of adapting classroom lighting conditions automatically to improve comfort and energy efficiency. Thank you. Hello, my name is Devina Kalisai-Narsono, and next I will explain CapCut 7, which is the implementation of static and dynamic data storage in our adaptive classroom lighting system. Static data in this program is implemented using constant variables like out_high 800, out_mat 400, in_dark 300, and in_comfort 500. These variables store fixed lighting threshold values used throughout the program. Since the values do not change during execution, they are categorized as static data. These constants act as environmental standards that help the system determine whether the classroom is too bright, moderately lit, or too dark. Dynamic data is implemented using a dictionary and a list. The dictionary stores the classroom's name, while the logs list dynamically stores all simulation results generated during program execution. During every loop iteration, the system creates a new dictionary called row. This dictionary stores changing data such as loop number, outdoor light intensity, indoor light intensity, blind position, and lamp brightness. Then data is then appended into the dynamic list using history logs append row. This allows the program to continuously accumulate new lighting records during each simulation loop. So overall, CapCut 7 is implemented through static data using constant variables and dynamic data using dictionaries and lists that are stored changing environmental lighting results during program execution. Thank you.
Hello, my name is Muhammad Taila from Group 7, and today I'll be talking about the sub CPMK number 6, which is conditions for our program or code for the case study number 2. I'll just go by it over quite quickly. Perhaps if I explain too much, it'll take too much time. So basically, conditions in this CPMK is implemented through conditional selection structures using if, elif, and else. The adaptive lighting system uses these conditions to analyze environmental brightness levels and determine appropriate lighting responses. And a simple way to put it, we have inputs and outputs. If those inputs meet the conditions or perhaps set parameters in a certain way, then a certain outcome will be produced. So we have two functions, which is for the blinds and for the lamps, that uses conditions. So first of all, we have the determine blind function, which evaluates outdoor light intensity to determine the blind position. So as I said, we have these parameters set, and if the input meets those parameters in a certain way, then the outcome, which is the blind positions, will be set. So as showed, if outdoor light is greater than the underscored high, then the blind will be assigned to the variable closed. Also, if the outdoor light is greater than the outside light, which is underscored mid, then the blind will be half open. Else if both two previous conditions are met, then it'll be fully open. Logically, it could be explained very intuitively, quite easy. So if the outdoor light is quite high, then the blinds will be fully closed. But if the outdoor light is at a medium level, so sunlight goes in, but it's still kind of dark, then perhaps blinds partially open. But if there's barely any outdoor light coming in, then the blind will be fully open. Uh, and we have another function, which is the determine lamp function. It evaluates indoor light necessary to determine artificial lighting levels. It's quite similar to as how it works to the determine blind function, and the logic is also pretty simple. Basically, if we have a dark classroom, then the lamps will be set high, be lit up, and if the classroom is not very dark but not very also bright, it's a moderately lit classroom, then the lamp will be at a medium intensity. But if the classroom is bright enough, it's at a comfortable brightness, then the lamp could be turned off. And as I said, it works quite similar to the determine blind function. If indoor light is less than in underscore dark, then the lamp level is set to a variable high. Also, if indoor light is less than in underscore comfort, the lamp level is assigned to the variable medium. Also, if those previous uh, conditions are met, then the lamp level could be turned off. And there's a missing part here at the end, which is the return. Basically, it's just based on these conditions, what is met, what conditions are met, whether it's the if, elif, or the else condition is met, then that data will be transferred to the variable blind and lamp level, which will be later on used for the next part of the codes. And yeah, perhaps that's it. Thank you.
On this slide, we explain the function used in our adaptive classroom lighting system. First, we divide the system into smaller modular functions, so each function has a specific responsibility. The first function is determine blind outdoor light. This function decides the position of the blinds based on the outdoor light intensity. For example, if the sunlight outside is too strong, the blinds will close. The second function is determine lamp indoor light. This function controls the lamp brightness according to the indoor lighting condition. If the classroom is too dark, the lamp brightness increased. The third function is applying lighting blind lamp level. This function combines the results from the previous function and produces the final system response. By separating the program into functions, the code becomes more organized, easier to understand, easier to debug, and more efficient.
Next, I will explain subchapter MK5, which is the implementation of basic input and output programming in our adaptive classroom lighting system. Input in this program is implemented using the input buka kurung tutup kurung function, which is user underscore out input enter outdoor light value and user underscore in input enter indoor light value. These inputs allow the user to manually enter outdoor and indoor light intensity values. The data entered by the user represents environmental lighting conditions inside and outside in the classroom. After receiving the input, the program converts the values into integers using outdoor values integer user out, indoor values integer user in. This conversion is necessary because the program needs numerical values to perform comparisons and decision-making processes. Output in this program is implemented using several print statements. For example, print action taken action. This displays the adaptive lighting response generated by the system, including the blind position and lamp brightness. Then program also displays system information and simulation instructions. For example, print lighting system start and print please enter data for 3 loops. At the end of the simulation, the program outputs a final summary log, which is print round log num outdoor log out logs. This summary shows all lighting conditions and adaptive responses recorded during program execution. So overall, subchapter MK5 is implemented through 1. Receiving environmental lighting data using input. The second one is processing the data, and the last one is displaying adaptive lighting results and summaries using print statements. Thank you.
Okay, so now I will explain how the loop code works. So first, we use for. For is used for looping and or iterations, and then the round number. So the round number is the number of rounds or loops, and in range 1 to 1,4. So this range is used to tell that the loop will end before number 4. So that's why the loop is looping for 3 times. And then we print the round dash num to show the user what loop they are in. And then the user will input their light value, the outdoor and indoor light values, and then those light values will be converted into integers by the program, and then it will pass down to the current blind, the current lamp, and after that pass down again to the action taken. So the lighting will be applied based on the current blind and the current lamp, and then print the action taken, and the user will see the summary and see the action taken by the program. Thank you for listening to our group's presentation. Hope you have a great day.